All right, in this video, we're covering the last example of a growth model, which is logistic growth. So logistic growth is what happens when you have exponential growth, but some kind of natural phenomena that limits that growth. That natural phenomena creates what's called a carrying capacity. Here we go, get my screen. So carrying capacity is the maximum population a habitat can hold. Okay, and so that limits the growth, right? We're not going to grow boundlessly. So in the fish example, say you have 1,000 fish that are in a lake, and we find out that without constraints, they're going to grow 10% per year. But maybe the lake it's physically bounded. It's got a carrying capacity, and maybe we can determine that the capacity is 15,000. What logistic growth does, it says, hey, my growth rate is going to be limited by that. So the growth rate, instead of being just R, it's R with some factor of the previous population divided by the carrying capacity. So we'll call that capacity K. And so in this fish example, P0 is 1,000, 10% is the R. As a decimal, we're going to have to write that as 0.1. And capacity is K. So we could set this up as Pn minus 1, adding the same. Notice if I just leave this the same, if I say like this, it's the same problem, but now I'm going to multiply a factor that reduces the growth rate, Pn minus 1 over K, which is 15,000. And for this, I will put in R, 0.09. Oh, no, 0.1. Okay, so to find out the population at year 1, we would take P0 plus 0.1, P0 times 1 minus P0, 15,000. So if my initial population was 1,000, we could find this out to be 1,000 plus 0.1 times 1,000 times 1 minus 1,000 divided by 15,000. So notice this term here it's not that big. It ends up being 1 over 15. So we got 1,000 plus like what would have been the normal 100 growth, but it's times some slightly smaller term. So we could find that out in our calculator. So initially, we got 193 trout or fish in the lake at time P1. Compare that with previously we had 1,100. So notice the growth is limited a little bit, but that growth will be limited even more so as we get higher population. So P2 would be P1, this value here, plus 0.1 using this formula here, times P1 times 1 minus P1 over, 15,000. And so by putting in P1 as 1093, you could find out what P2 is, and P3 and so on. The interesting thing with this model is there is no explicit formula. There's no explicit formula that you can do. So the best we can do with this, it's called a discrete logistic model, is use the recursive. That's all we got. Unless we can model this phenomena as continuous, that means fish are being multiplied continuously, which is often the case. Then there is a explicit equation for this, where T is the time, K is the carrying capacity, and A and K are derived from the situation. So we're not going to use this model in this class, but you'll probably see it in biology or other situations. And so you see the difference here. Exponential growth will continue. That's what an exponential curve looks like. Logistics starts the same. It starts to increase quickly, but then it slowly levels out and then reaches what's called the carrying capacity. So there you go. That's logistic growth. Good to be aware of. Just 1 or 2 problems on the homework on this problem. All right, that wraps up our 3 sections on growth models. See you next time.